Alright, let's get into infinite limits. So, here's a limb. I'm just going out on a limb here. Sorry, I should never start these with puns. So let's talk about as something approaches infinity. And why do we care about infinity? Why can't we just plug it in? So let's first, what is this even saying again? Just to remind ourselves, if you have some kind of curve doing its behavior or whatever, eventually it will either slow down to one result or it'll just go way to infinity, or yeah, slow down to one result or go to infinity. That's kind of the two behaviors that can happen on any curve. Slow down to a result, go to infinity. So the idea of infinite limit is to find, does it slow down, does it calm down after a little bit to one result, or does it go all the way to infinity, or it could go to negative infinity. We can't forget that. Those are the two behaviors we're gonna talk about. And so that's why you use an infinite limit. Infinity is not a number, as you might think. And we're talking about calculus infinity. There's kind of different ways you can think about infinity. But calculus infinity is talking about approaching things. It's talking about, hey, if you look at this, what's happening to the curve? I mean, if you look at 1 over x, yeah, you could say it never touches 0, but what's happened in the curve? It's approaching 0. So we say the limit of 1 over x, for example, is 0. That's the purpose of an infinite limit. It's just say that certain behaviors happen at certain points. And knowing the overall behavior of a limit is important for identifying aspects of functions, especially when you can't graph it. Graphing it kind of gives away some material. It's like, oh yeah, this is of course approaching 0, but if I gave you this from the get-go, you wouldn't necessarily know for sure that that does. So it's all about saying, hey, at the end of things, imagine that there is an end. Somewhere on the line, you're going to actually finally touch 0. And that point is infinity. That's what that limit is telling you. Now, it's not an exact number because this never actually touches 0 in a general sense, but it does exist. So that is when it calms down. There's other things. And then you can also use them to find, hey, what does this actually go up forever, or does it finally calm down? So if you have some, I guess this kind of looks like e to the x, so let's just call it e to the x. What's the limit as x goes to infinity of e to the x? Guess what? It's probably exactly what you'd expect, infinity. And that's also a cool thing about limits. You can have infinity as a result. It's not wrong whatsoever. And so this situation happens more than not because most functions that you know grow. So even absolute values, or even so any exponential, any ln logarithm, any just simple polynomial would go to infinity or negative infinity. To make them go negative infinity, just make all these negative. But infinity in general is the behavior of most functions. But if you start combining sometimes they calm down after a certain point. So dividing by x would do that, and multiplying by a logarithm that would do that. And so there's all sorts of ways to talk about it, but yeah, this is what we care about. And behavior, that's actually what we start calling this. How does it behave? What happens at the end on the function? And you're probably thinking, okay, okay, I get it. But there's also negative infinity, so you have to also care about what happens on this side of it. All right, so those are the two cases we care about: positive and negative infinities, and those are infinite limits. Now, it just so happens that L'Hopital is your biggest ticket through the door for talking about behaviors on infinite limits. And so here's what I mean. Let's have something approach infinity. How about, let's see here. What could we say? So x squared plus 2x over x cubed plus 3. What happens when x goes to infinity? That's what I care about. If you were to graph this, you might get some kind of shape. But does it go to 0? Because honestly, if you plug in, I don't know, this guy gets really big, this guy gets really big, but how do you know which one gets bigger faster in a general sense? I keep saying general sense for some reason. But how do you know which one gets bigger faster? Well, guess what? Let's just evaluate at infinity in a sense. Oh, I keep saying in a sense. I need to stop that. So x goes to infinity. So at infinity, guess what? These both go to infinity. And at infinity, guess what? This also goes to infinity. The only time when it really matters is whether it's positive or negative. But which one does it go to? Because infinity over infinity, if the top gets bigger faster, then this will go to infinity. If the bottom gets bigger faster, then this goes to 0. But if they both get infinity at the same rate, you're going to approach some limit. There is a limit value for this. And so which case is it? We don't know, so let's take the derivative. Because we can. This is a case where we can. So derivative of that is 2x. Derivative of that is 2. Derivative of that is 3x squared. Derivative of that is 0. My bad. We don't have that. And if you plug in infinity to this, you still get infinity over infinity. So guess what? We can keep using L'Hopital's rule. It's really a repetitive thing with these kind of problems. So what happens? Derivative top, that's 0, that's 2. Derivative bottom, that is 6x. Yep. And you can kind of ignore the 2, 6, because what happens when you divide by an x, and x goes to bigger and bigger values? Well, this is one of the most well-known limits, and so if you can get it in this form or anything like it, then you will be certain this kind of thing happens. If you get 1 over x, anything divided by x, as long as there's not some other function here, it's always going to be 0. Same with x squared, same with x cubed, same with x to the 4, same with x to the 5th, because those will just get smaller faster. So that's what we know about those kind of functions. So if this ever simplifies to something like this, we know this goes to 0. Even though that 2, 6 is there, that just means it goes down. If anything, that means it goes down faster than 1 over this, because 2, 6 simplifies to 1/3. So you're multiplying your values always times 1/3. So rather than 1 divided by x, you get 1/3 of that height. It won't look exactly like that, but you get the idea. So that's what we're talking about. And let's try another infinite limit. Let's try an easier one. I mean, let's... I don't know, I kind of noticed something here. If the top is greater than the bottom, and you keep taking derivatives... I mean, if the bottom is greater than the top, and you keep taking derivatives, seems like one of these will run out of derivatives to take. And so, when it runs out of derivatives to take, the bottom will still have a few derivatives, as we saw here, because the power is bigger, and so it's going to be decreasing before this guy decreases. So by the point when you can't do L'Hopital's anymore, just because you already know that plugging in infinity would get you 0. So this is kind of like your final stage. But if this guy is bigger than this guy, what happens? It goes to 0. And that is a limit rule people tell you without ever justifying it. They just tell you, like, look, the bottom has a degree. That's what we'd call that first polynomial. The n is bigger than x to the m, then plus something something, plus something something. And we're saying that the power decreases as we go this way. If m is less than n, it has to be less than, then what happens? It goes to 0. There you go. So that's the first limit rule, and we showed it with L'Hopital's rule. What's another thing that you think is probably true? Well, let's investigate the case if the top is larger. And you probably have an idea. The top is larger and you keep taking derivatives, it'll probably still be in existence. But let's at least see it in action. So let's come up with some random kind of... Actually, it won't be random, but whatever. So as x approaches... By the way, it doesn't have to be x, as we already saw when we proved some other derivatives. We sometimes use the limit to talk about it just in a very generalized sense. But as x approaches infinity of x to the 3 plus x, yeah, plus 2, sure. Then let's make this x, yeah, good enough. Definitely good enough. Now this might have some wonky stuff happening because you're dividing by an x, and so you could factor everything out to divide by x and see what happens. But at infinity, what does this become? Well, let's see. If you plug infinity into the top, that gets you a positive infinity. In fact, let's make it negative, just so we can say that, okay, I know this goes to negative infinity. The first term always dominates because it has the biggest power. And the bottom also goes to infinity. So this is a L'Hopital's case. Even though I made it negative, that doesn't really matter in this case, because we can still use L'Hopital. Alright, x approaches infinity. Derivative of the top is 3x squared plus 1. It's kind of nice how easy derivatives can be. So don't ever forget that. Derivatives are nice. And bottom just becomes 1, right? So this is the limit as x goes to infinity of negative 3x squared plus 1. And so what happens here? You can basically ignore the one that's only changing a little bit. This, in general, you can also ignore the 3. This is an x squared. It has an x in it. If you plug in infinity into this, it goes to infinity. Except one little thing, negative infinity. And that's one of those cases we talked about at the beginning. It is one of those common, it turns into one of those common functions, x squared would be included, that goes to infinity or negative infinity in general. Only when you start dividing and messing with some of the order of these do you actually get finite limits. But we so what our conclusion here is if x approaches infinity of some x, some x to the m plus stuff over some x to the n plus stuff, it's going to, and we also have to say m is now greater than n, not equal to, then it goes to positive or negative infinity. We have to say that this could be positive or negative. Alright, so that's the important thing to note here. And sometimes the bottom being negative can influence this infinity being positive or negative, but that's what we care about here. Now, last case, what happens if they're equal? I recommend you try this for yourself, try to make up a problem. But if they're equal, this is an interesting thing that happens. So 3, let's say x squared plus 2x plus 3 over 4x squared minus 3. There you go. Alright, we already know that's infinity of infinity case. I specifically made it that way. So take the derivatives. Alright, draw the top. That is 2 times 3, 6, x. And then plus 2. Draw the bottom. That is just 4 times 2. That's 8, x. Alright. Plug in infinity. You still get infinity. So let's take another limit. L'Hopital's should start seeming pretty easy by this point. Alright. You just have to check if plugging in actually gives you a indeterminate result. Derivative of the top is 6. Derivative of the bottom is 8. So our thing converges to 6/8. There's no x in here, so we don't have to care about behavior here. It's just 6/8, which simplifies to 3/4. Right? So this limit is 3/4. If you were to graph it, it might do some crazy behavior here. But at infinity, it calms down to a value of 3/4. And so, and if you notice, what is the first term here? 3. What is the first term here? 4. So it just used these two values right here, and it gave you it. And it should make sense that any value here will just be divided for the limit. And that is a limit rule people also will tell you when you're learning limits. So, let's conclude here with our findings. Sorry, I'm just making sure. Don't waste a page here. Aha, here's the page. Alright, I'm going to replace my sheets later. Alright, here we go. So our conclusion, let's write them all up. If our limit of, let's say, ax to the n over bx to the, oh, I said this first one was m for some reason. The second one is n plus stuff that's decreasing in degree. So that's the degree of the top, that's the degree of the bottom, the n, and m is the degree of the top. Limit as x approaches infinity. Could be negative infinity as well, but I think you can logically figure out what those happens on those cases. If m equals n, then it is equal to a limit. Alright, usually we just write an L. And that limit in this case, because they were O and B, is a divided by b. Alright. Now, no, we don't have to rewrite this. Now, if m is greater than n, if the top is, then it goes to positive or negative infinity. You can use some logic through that. If the top or bottom is negative, then that will influence it. If they're both negative, then it will actually become positive. But you can use logic for that. And last case is n is greater than m. If the bottom is greater, then it goes to 0. Alright? And these are limit rules that they tell you without proving it because they don't want to teach you derivatives. And I think that's kind of silly, but whatever. It kind of makes sense for the sake that, like, the idea of calculus sounds scary to a lot of people. And so making people learn calculus before they can learn limits seems strange, considering, in a sense, derivative is a limit. Alright, for the rest of this video, I will correct my mistakes from earlier. My imprecise results. So let's start with summation. What did I do wrong about summation? We said, I don't know, I keep going back to this case. Now let's talk about the 2/3 case. I like that. Alright. 2/3 to the I. Man, that's sloppy. And I equals 1 to infinity. And we said that equals, what did we say? We said, I think 2. Yeah. We could check that, but I don't feel like it right now. What did I do wrong here? Here's what I did wrong. You have to approach infinity. Infinity is not a result you can just plug in. With summation, you are kind of plug in. And so this is improper. And as you can guess, something similar to it is like that integral. Integral from 1 to infinity of pi 1 over x squared. We talked about that guy. That guy converges to pi. But this is also known as improper. Now that I care too much about being proper, let's at least talk about why we call it improper. And it should be pretty clear. It's all about that infinity. Because you have to approach infinity. You can't just say, okay, at infinity. And so how you'd actually write this is with a limit. Let's make it always to n. We don't have to, but we can. So let's say as n approaches infinity, n is just a value, so we can plug that in, of this fraction, the limit of the summation, sorry, you can see that. So we make n the top thing instead of infinity, and we let n approach infinity. Well, that equals 2. The limit equals 2, because we have to approach this summation result. Same with an improper integral. We have to take the limit before it. As n goes to infinity, you could make it anything. In fact, let's make it like k for a second. As k goes to infinity. So you can make this top result k, and this bottom number 1, and pi 1 over x squared dx. And we said that's equal to pi. And this is always a better way to write these. Because infinity is, again, we're not plugging in infinity as a result necessarily. I mean, it usually makes sense to when we're solving it, but lots of cases infinity does not behave like we want it to. And limits is the only tool we have to talk about it. And so writing them like this is always preferable for mathematicians. Not that you have to consider yourself a mathematician when you're doing this stuff. It's just like, we have to be a little more honest about what we're actually doing in these cases. So you'll see that a lot, show up a lot. In fact, I think I mess with infinity a lot more than I should, for the sake that lots of things are not easy results at infinity. So just remember that this limit case is usually preferable. So if you're doing an exam or something, you're probably going to want to write limit as something approaching infinity, not just infinity. But you could be improper if you want. Your choice. So that's infinite limits, and that's limits in general. You're always approaching results. Something I didn't cover is sometimes limits don't exist. In fact, let's just go over that so I can be done with limits. All right. Let's just use the rest of this paper. I'm almost out. 2 sheets left. All right, so let's just talk about when the limit doesn't exist. All right. Here's a case where a limit doesn't exist. Remember that approaching infinity, we can't really use L'Hopital's rule here. So sine x, all right, what happens at infinity? Sine x looks like this, and it never changes. It's always oscillating. So at infinity, what happens? Well, nothing. It could be this. It could be this result. It could be this result. It could be any of these results between -1 and 1. All right. So our y value could be between all those results. And here's the key thing. If the limit of something could be multiple results, then the limit, there's not really an easy way to write this. The limit does not exist. All right. Does not exist. You just can't have, if things exist with 2 results or more at one point, then it does not exist. And so that is an example. Same with cosine, same with tangent. All of those, it does not exist because it doesn't stop oscillating at some point. However, if you divide by x, this would actually be 0. And so you have to be careful, but that's just because x, dividing by x, actually makes this curve get smaller and smaller. Even though it's oscillating, the distance that it oscillates between gets smaller, and that's what we care about. We can't have something like this happening. And what's another case where it does not exist? Let's talk about absolute value of x divided by x at 0. If you graph this, let's plug in 1. If you plug in 1 divided by 1, absolute value of 1 is just 1. So you get 1. At 2, you get 1 because absolute value of 2 is 2, and divided by 2, it's 1. So you're going to get 1 for all positive results. And then negative results, if you plug in -2, you get positive 2 on top, right? And you get -2 on bottom. And so the 2's cancel out to be 1, but it's a -1. And if you think, oh, this is kind of a random case. Well, actually, interesting enough, it is the derivative of the absolute value function. Because the absolute value function has a constant -1 slope over here and a constant 1 slope over here. And so the derivative, at the point 0, there are 2 values here. If you approach from the positive side, which you can do, I don't really talk about that much, but you can approach things from one side. Well, if you do that, approaching from this side is 1. Now, if you write the limit as x approaches 0 from the negative side, guess what? The limit is a -1. And this is one way that you can prove that a limit does not exist. If approaching it from 2 sides warrants 2 different results, then that means that the limit does not exist. That's an arrow. All right, makes sense. This is called a discontinuity as well because it isn't continuous. If you're walking along, then you teleport all of a sudden over here, this is a discontinuity. And it's also known as a point when limits do not exist. And a use for finding when limits do not exist is when derivatives do not exist, because derivatives are kind of limits. And so, for example, the derivative of this guy does not exist because this limit does not exist. All right, so that is the idea here. You get a lot of scenarios where limits don't exist as well, but again, they're kind of cherry-picked. In general, it's all, if you approach infinity, it's always going to go to infinity or negative infinity in general. And at finite values except 0, 0 is usually a weird guy. it's going to do some crazy, it's going to usually converge to a result if it's at a specific value. Just the weird cases show up. All right. Thanks for watching these, and yeah, that's limits. So if you ever see limits, that's what they do. Just approach a value. Thanks for watching in.